Hello everyone, and welcome to today's webinar in the CERDP and ESTCP webinar series. My name is Rula Deeb. I'm a Senior Principal at Geosyntec Consultants in Oakland and the coordinator of the webinar series on behalf of CERDP and ESTCP. I will be facilitating today's call. Today's event will consist of a brief overview of CERDP and ESTCP, followed by the technical portion of the webinar. Our webinar today will focus on energy sustainable wastewater treatment systems for forward operating DoD installations. First, Dr. Catherine Guy of the Army Engineer Research and Development Center will talk about alternative wastewater treatment technologies and distributed low energy wastewater treatment for fuel generation and water reuse. Catherine will also discuss federal policies and mandates that support related research efforts. Catherine's presentation will be followed by a brief question and answer session. Following Catherine's presentation, Dr. Pat Evans from CDM Smith will talk about energy sustainable wastewater treatment systems based on microbial fuel cells for forward operating bases. Pat's presentation will also be followed by a Q&A session, and we will conclude the webinar with an interactive Q&A session with both of today's speakers. Today's broadcast will be listen only. You may submit questions by using the chat box on the left-hand portion of your screen. You do not need to wait until the Q&A period to submit your questions. In fact, we encourage you to submit questions as you think of them. On this slide, we have provided a few suggestions in case you experience difficulties with the broadcast audio. Typically, any delay will be fixed if you just refresh your screen. Alternatively, you can call into the conference line shown here. If you continue to have problems, please submit a comment using the chat box in the lower left corner of the screen. With that, I would like to introduce Dr. Andrea Leeson, who is the Deputy Director of CERDP and ESTCP and also the Program Manager for the Environmental Restoration Program area. Andrea has been with CERDP and ESTCP since 2001, and before that she served as a research scientist at Battelle's Memorial Institute, where she conducted research on in situ bioremediation. Andrea?
Thank you, Rula, and thank you everyone for joining the call today. Before we jump into the technical talks, I just wanted to give you a little bit of an overview of CERDP and ESTCP and talk a bit about some upcoming events and webinars that you may be interested in. Slide 9. First, CERDP is our Strategic Environmental Research and Development Program, and we were established in 1991 by Congress as a partnership between DoD, DOE, and EPA. And primarily this is research and development, with much of the research being conducted in laboratory settings, but always with the end goal in sight to impact real-world environmental management. Slide 10. ESTCP is our Environmental Security Technology Certification Program, and in this program we're demonstrating the knowledge and the demonstrations or technologies that have been developed under CERDP and have matured into ESTCP and are ready to be developed in the field. And our goal really is to promote implementation of those successful technologies and to facilitate regulatory acceptance. Next slide. We have 5 program areas. 4 are in ESTCP, 5 in CERDP. Environmental restoration, installation, energy and water, munitions response, resource conservation and resiliency, and weapons systems and platforms. All of these, other than the installation and energy and water, are both in CERDP and ESTCP. Installation, energy and water is only an ESTCP program, but we manage these 2 programs very closely using a designated program manager for each area under both CERDP and ESTCP, so we're very closely aligned. Slide 12. The webinar you'll see today was conducted under the Environmental Restoration Program area. We have essentially 5 main focus areas in environmental restoration: contaminated water, contaminants on ranges, contaminated sediments, wastewater treatment, and risk assessment. And of course, the work you'll see presented here today was conducted under a wastewater treatment focus area. Slide 13. We have been doing our webinar series for a couple of years now, and we have found it a really wonderful way to get the word out about the various technologies we're supporting. Shown here, you can see the number of webinars that are coming up. The next webinar from the Environmental Restoration Program area will be on October 4th, and it's going to highlight results from a strategic workshop we held this summer dealing with contaminated groundwater, specifically the chlorinated solvents, but some contaminants that we find commonly in groundwater at DoD sites. Registration is open now for these webinars. You can go to our site and register for the one that's most of interest. Everything is listed at the link that is shown on the slide here. Slide 15. Finally, before we jump into our talks, I also just wanted to mention our symposium. We are holding it again this year from November 27th through 29th. I'm very happy that we will be holding it again. It is a great opportunity to see results from everything we're funding in all the program areas. Registration is open for the symposium, and I hope you can join us at that meeting. At this point, I'll turn it back to Rula, and thank you.
Thank you, Andrea. It is now my pleasure to introduce our first speaker, Dr. Catherine Guy. Catherine is a materials engineer with ERDEC's Construction Engineering Research Lab in Champaign, Illinois. She has led efforts to develop distributed wastewater systems as alternatives to centralized treatment, and also for contingency basing to help the DoD meet energy and water reduction goals. Since 2010, Catherine has worked on a 3-component system using anaerobic digestion, ion exchange, and ammonia electrolysis techniques. Recently, her research has expanded into thermochromic paints for building energy savings and in-place mold preventive coatings. Catherine received her bachelor's degree in chemistry and math from the College of William and Mary, and a doctoral degree in chemistry from the University of Illinois at Urbana-Champaign. Catherine?
Yeah, thank you for the introduction. She mentioned my name is Catherine Guy, and work for the Army Corps of Engineers out of Champaign, Illinois. On slide 17 is the agenda for what I'll be talking about today. I'm going to start off with federal requirements and regulations, especially how they affect the guidance on reducing water consumption, energy usage, waste generation, and it's not going to be a comprehensive overview, but at least some of the main ones that we look at. In the second half of my talk, I will be discussing a project under ESTCP for distributed low-energy wastewater treatment for fuel generation and water reuse. And I'll wrap up with a little bit about why the DoD cares about reducing water energy usage and reducing the amount of waste generated. Slide 18 has a list of some of the most common federal requirements and regulations. The federal requirements and regulations is an ever-changing landscape, and comes down from the President, comes down from the various services, and even public laws. Slide 19 goes into the first executive order I wanted to mention today. And this is planning for federal sustainability in the next decade. This looks at calling federal agencies to have a numerical number, trying to replace a portion of their electrical energy, or reducing the amount of energy they use, but also replacing it with renewable electrical energy. They also look at water. How can we reduce the amount of water? And how can we go a step further and look at stormwater and wastewater management? This executive order was great in the sense that it had a deadline, 2025, and an actual goal number. However, this year, on slide 20, it was replaced with a new executive order. The executive order signed this year removes a lot of the goals, the actual numerical goals, but makes it more flexible for the individual agencies and installations to set their own programs to figure out how they're going to accomplish the reduction in energy and water and waste. They also focused on enhancing infrastructure and operations resilience. How can we maintain what we have and not be dependent on a single source? And this will enable effective mission accomplishment. So in addition to reducing electrical energy from typical sources and replacing it with renewable, they want to replace potable water with using non-potable water consumption and still comply with the stormwater management requirements and implement waste prevention. How can we reduce the amount of waste generated, but also how can we recycle it? How can we prevent it from going into the landfill? On slide 21, move into some of the Army directives. The Army directive for net zero installations addresses energy, water, and waste, and really focuses on reducing all of them as possible. One of the ways to address the energy is through renewable energy, solar, and other such electrical generation, but also to implement energy recovery. A lot of focus has been on waste heat from generators and trying to use that instead of reheating the water from baseline. Water efficient technology, again, reducing the amount of water used. Also the call to come up with ways to reuse water. How can we send water from potable, use it once, recycle it, whether it's for a lower tier use or for getting back up to potable. And then on the waste side, reducing solid waste, but also can we use the solid waste as a resource? Can we generate energy from it? Or can we turn it into another product? This way it doesn't go to the landfill. And slide 22 is another Army directive that we often refer to. And here it's moving a little bit more from the environmental side of why it's good to reduce energy and water consumption into maintaining our mission, maintaining the Army mission and maintaining the ability to do its mission through having energy and water access. The Army Directive 2017-17 maintains that for critical missions, an installation should have energy and water supply to less than 14 days. And this is within the fence line, so not dependent on local power grids or water treatment plants. In addition, for all missions and on a daily basis, the Army Directive moves the Army to having assured access to a resource, whether it's energy or water, and doing this through maintaining multiple sources, using sources that aren't typically thought of as a water source maybe, going to more renewable energy, things that can be generated on site, and also looking at reliable infrastructure condition, maintaining what we have, fixing what's broken, and putting on-site energy and water storage, batteries, water tanks that are within the fence line so that we're not dependent on the surrounding community. An important part of this is flexible and redundant distribution networks, making sure that should one point go out, that the rest of the installation can still receive the power or the water that they need. And together this will allow the Army to reliably meet its mission requirements and continue operations even in emergencies. In slide 23, it's the Energy Policy Act of 2005. The public laws look at more broadly outside the federal government, but have some specific requirements for federal government. Public Law 109-58 starts looking at energy efficiency and improving energy efficiency through making statutory standards, requiring the federal government to have specific actions. Some of these were surveying the buildings and doing life cycle cost analysis and payback time frames. And also under the public law, they provided incentives for voluntary improvements that went above and beyond the minimum requirements. This public law also focused on renewable energy, increasing its production use of currently known technologies, but also doing some research into advancing the technology, coming up with new ones, and finally working to promote commercial development, actually making a product that people can buy and use in the facilities or in the buildings, in their homes, so that it goes beyond just an idea and a prototype to an actual object. Slide 24 is the Energy Independence and Security Act of 2007. This public law expands on the previous one, looking for greater energy independence and security for the United States. Again, what can we do within our borders to maintain the energy that we need to operate as we, in current status, reducing our dependency necessarily on foreign supplies, but also developing greater capabilities within our borders. So we increase and develop clean renewable fuel production, still putting some focus on research, especially for greenhouse gases, whether we're capturing and storing them or possibly converting greenhouse gases into a fuel source. While a lot of the things under Public Law 110-140 focus on commercial sectors for vehicles and electrical appliances, the federal government wasn't exempt and does have requirements for energy performance, but overall public law looks to increase the U.S. energy security. Slide 25 describes really why research is needed in these areas. A lot of the requirements and needs and information gaps that I discussed are great on paper. They meet our goals of reducing costs, saving our resources, getting security, but they're ideas, and in order to actually implement them, we need to have something that can be bought, purchased, installed, or a program to be used. And this is where research comes in. It's the linchpin between the two sides. On slide 26, the project we have currently funded under ESTCP helps fill in some of this research gap. The D-LEWT project is distributed low energy wastewater treatment. And we're going to be demonstrating a decentralized wastewater treatment system in a standard shipping container that's capable of treating 1,000 gallons per day. It's going to do this in a low energy manner, but also generate fuels of hydrogen and methane that can be used to supplement the electrical usage of the wastewater treatment or be used somewhere else on the site. We're going to validate the system compared to similar systems that operate in an aerobic or oxygen-rich environment to show that our technology has reduced energy consumption, reduced sludge production, and has effluent able to be reused. So this project really addresses the energy, water, and waste parts. On slide 27 is a pictorial representation of what I just discussed. On the left side, we have 1,000 gallons per day coming into the D-LEWT system, shipping container box. The up arrows represent the methane and hydrogen fuels that are generated. Out the right side, the effluent is water that's available for reuse. And we can take the harvestable fuels and put it back into the D-LEWT system to increase the energy efficient operation. On slide 28, I have the technology description of our D-LEWT system. The D-LEWT system integrates 3 technologies to treat wastewater, reduce the energy consumption, and generate useful fuels. The red box at the top is our first step. It's an anaerobic membrane bioreactor. This takes the organic matter and converts it into methane. It's lower energy compared to aerobic or oxygen-rich systems, but it doesn't address the nitrogen component of wastewater. From the amber, we get a nitrogen stream. It goes into ion exchange, and we use a natural mineral in the ion exchange to collect the ammonia and remove the ammonia from the system in a concentrated solution to send to ammonia electrolysis. Ammonia electrolysis applies a small voltage to some catalyst and generates hydrogen gas, which is our second fuel. On slide 29, I have a more detailed schematic of the D-LEWT system. If we walk from left to right, wastewater comes in, again goes to the AFMBR system. In here, during our project, we're going to be monitoring the volume and composition of methane gas produced. From there, we go to cleanup to light. Again, this is going to be to capture the ammonia. Once the water has gone through the cleanup to light, it comes out as the effluent, the treated water, and is available for reuse. The cleanup site is then coupled with ammonia electrolysis for regeneration of the mineral to remove the ammonia, sending the ammonia to ammonia electrolysis on the far right. The ammonia electrolysis cells break the ammonia into hydrogen and nitrogen gas. So nitrogen gas is our byproduct here, which being a major component of the atmosphere, it's safe to release. We keep the regenerant solution in a closed loop between the cleanup site and the ammonia electrolysis cells, so the regenerant doesn't become a waste product in our system. On slide 30, the current status of the anaerobic membrane bioreactor. We were really lucky with some partners at the University of Illinois. They had the system available and they were willing to let us use it for the project. They've updated the controls and added a new membrane. At this point, we're ready for integration to the total D-LEWT system, pending some contract negotiations and actually getting the system built. On slide 31, the second step of the system is a clinoptite ion exchange. As I mentioned before, clinoptite is a naturally occurring mineral. It's mined in the U.S. and across the world. The system is nearly complete. We sent it out for an engineering firm to build it for us. We have 4 columns, similar to the one shown at the very bottom, made of clear PVC pipe. This way we can see what's going on in them. And one of the big advances is actually putting an autonomous operation in for valve positioning and timing. Currently, for the lab model, we have to have a student in there flipping switches. But for deployable operation, that's not going to work. So we're really excited to have this autonomous operation and control system. On slide 32, I show a picture here of what some of the electrolysis cells look like. Between 2 of these plastic plates, there's a water-permeable membrane with catalyst on it, and that catalyst, when voltage is applied, does the work of breaking the ammonia into nitrogen and hydrogen gas. We've obtained an additional 12 cells from Ohio University. They hold a patent on this technology, and so far the only ones who are making this cells. And this portion of the D-LEWT system is also awaiting integration into the complete system. Slide 33 shows where we're headed in the future. Hopefully early next year we will have our system complete and ready for deployment to Mountain Home Air Force Base. Mountain Home Air Force Base has been great to work with. They have a headworks building that's going to be perfect for our project. There's a grinder and pumping station right there. And on slide 34, one of the nice things about this is that we have access to an open channel from which to draw the wastewater. Again, it's going to be post-ground, so it's going to be great to send into our anaerobic digester. And we can also situate the system so we can return our effluent, the water coming out of our system, right back into Mountain Home's wastewater treatment. This is great in case of system failure or system malfunction, that we're not creating a public safety hazard. The water is going to still be treated through a standard wastewater treatment plant. And this is not going to cause a problem for them because we're not drawing enough water to impact their wastewater treatment process. On slide 35, I have some of the numbers for our project in terms of what we're looking to achieve. I mentioned that we want to be lower energy, so we want to reduce our energy consumption compared to aerobic systems that use a lot of oxygen. We also want to produce hydrogen and methane fuels to offset some of the energy consumption. Together with reducing energy consumption and generating these fuels, our goal is to get to a net energy consumption that is 6 kilowatt hours per kilogallon less than a similarly sized aerobic system. Anaerobic systems are also known for having much less sludge, much less the biomass, and the water coming out of our system, we expect to meet some reuse standards. Shown here are just two of the parameters that we're going to be monitoring: chemical oxygen demand for some of the organic loading and the amount of ammonia that comes out of the system. On slide 36, just some recap what I was talking about with the D-LEWT project. We're going to be demonstrating a decentralized wastewater treatment system that generates methane and hydrogen fuels. It's expected to have reduced energy consumption, sludge production versus aerated systems, with water that can be reused. And overall, because we're addressing water, energy, and waste, it really helps support the energy and larger net zero goals. Slide 37, sort of subtitled as Why the DoD Cares, How the DoD Benefits. Number one is often save money. If they can do things cheaper, that's going to be a good thing. Save lives, especially when we're dealing with remote locations. The fewer convoys that we have to send in, the better. Mainly in operations emergencies, a lot of the Army directives I mentioned, we're looking at this in terms of having a supply on hand, redundancy, different sources, and along with that, meeting the regulations. We try to do our best. Again, a lot of it comes down to money. Can this save me money, or do I have the money to implement it? Adjust to diminishing supply, especially in areas where water is becoming scarce. How can we find alternative water, reuse the water that we have so that we're not drawing fresh supply? And because overall it is the right thing to do. On slide 38, for additional information, the project website and my speaker contact information is there.
Thank you so much, Catherine. I would like to remind our audience to submit questions by using the chat box on the left-hand portion of the screen. We have received a number of questions on this first presentation that Catherine will answer. So Catherine, we got several questions about the use of anaerobic MBRs. There's a lot of interest commercially, but there's data that suggests that biofouling could be a problem. So do you have any operational data that shows how you've overcome this issue?
I don't have any actual data from any of the projects I've worked on. I know some people are looking at alternatives, and I believe some of the work that others have done under Certified ESCP have looked at alternative arrangements for the bioreactors. Some of them includes gas scouring of the membranes. Membrane development to reduce the biofouling is always important as well. We're using a ceramic membrane, which I've been told by our ANMBR experts is a little more robust and can just be cleaned with back flushing. So.
Great, thank you so much. You mentioned the use of D-LEWT in your proposed system. How readily available is this mineral?
D-LEWT is found in many countries. In the U.S., it's sold actually for a lot of applications in terms of shoe deodorizers, kitty litter, and a variety of uses because it does like the ammonia so much. It's available in other countries as well, so wherever an installation or site might need it, there's probably something reasonably close by to access.
Great, thank you. This is really useful to know. A question from the Colorado School of Mines. How are you going to capture the dissolved methane in your effluent?
To be determined. It's something we're aware of, and it's something we are, with some additional funding from other sources, hopefully going to be developing better ways. There are some membrane degassers. Their effectiveness is, again, subject to fouling and subject to operational issues. For now, we're going to be capturing predominantly what comes off in the gaseous phase, with the awareness that we are losing some to the dissolved methane.
Great, thank you. how susceptible to environmental changes is the anaerobic digester, and are there environmental controls in the system that can deal with it?
Mm-hmm. Yes. We're going to be operating the system closer to ambient temperatures than a lot of anaerobic digesters. A lot of them try to be in the thermophilic, so hotter temperatures, but heating water is very energy intensive, so we're going to operate at lower temperatures. Wastewater itself has some heat in it, just coming from the typical uses where you generate wastewater, but we will have within the container, we will be maintaining a minimum temperature, I believe it's around 55 or 60 degrees Fahrenheit, just to prevent freezing.
Great, thank you. With regards to that energy demand, how much of it is from the ammonia electrolysis system?
The ammonia electrolysis system actually has a very low energy draw. We're applying 0.925 volts across the cells. Most of the energy for the ammonia electrolysis will actually be in pumping the water through, and we do have to heat that one up for efficient operation. But back of the envelope calculations show that we should offset it pretty well with the amount of hydrogen we can produce.
Thank you. Is it possible to add other organic waste, such as kitchen scraps, to the system?
Absolutely. Anaerobic digesters love organic waste and work best in concentrated streams. Wouldn't want to add too much of products that have a lot of fat in them, just because of floating and things like that. But a lot of the, vegetable scraps and things like that would be great to add to the system.
Thank you. Can you discuss the footprint needed for a full-scale system?
That's one of the things we're going to be determining in our demonstration. It's anticipated, like for the AnMBR reactor, the tank will scale pretty consistently with increasing flow rates. Within the cleanup site and the ammonia electrolysis, a lot of the equipment surrounding them is going to be the same when we scale up. Would just be maybe slightly bigger columns or a few more electrolysis cells. So I think the change in footprint is really going to be with the AnMBR footprint needed for the tank. So I don't have a definitive answer, but it's something hopefully, check back in a couple of years when we've done the demonstration, we'll have a better answer.
Sounds good. Thank you, Catherine. Do you have an estimate of how much methane could be produced from this system?
Not readily available. And some of it's also going to depend on what the concentration of organic loading is in the water. I don't remember at Mountain Home what their primary source of the wastewater is at this site, but the composition changes a lot with how much it's diluted by other processes, or whether it's from housing or from office buildings. So I don't know in our particular case what our methane output will be.
Thank you. A question from the Navy. For energy capture from the produced gases, what do you envision as the equipment needed?
We're looking at a couple different options. A lot of our calculations are based on, for methane, using as in a generator. We've also looked at burning it for turbines. Some of our discussion has focused recently on, can we merge the methane and hydrogen into a common stream to be used in a generator? What ratio will work, what won't, what's the energy performance loss. So we're really looking at a lot of technologies that already exist, possibly including fuel cells. If we can convert the hydrogen to a storable or a pressurizable system, fuel cells are great because they're quiet and clean themselves. So we're looking at a lot of those type of technologies.
Great. Two more questions before we transition to the next presentation. Do you have an estimate of the capital cost for this particular system?
Not yet. We're still really in the beginning stages of demonstrating it, and so a lot of our costs right now are in the engineering and design costs, so it's not fair to put those into the capital cost. But again, I guess when we complete the project, we'll have some good numbers for you there.
Thank you. And the last question is, can portions of this technology be used for applications other than treating wastewater?
Absolutely. We're looking, some towards agriculture, especially areas that produce a lot of animal waste that might have a very high ammonia or urea content. The electrolysis or clumped-light electrolysis system will be great there. AnMBR is used in various wastewater treatment plants, so there may be other technologies that can combine with it to use the ammonia in a different format. So really, being a three-component system is nice because we can perfect the technologies as a system, but also individually.
Thank you, Catherine, for a great presentation, and I just want to direct the audience's attention to this slide, which shows the link to Catherine's project's webpage, and as soon as project reports are available, they will be posted to that webpage. So make sure to refer back to her project landing page for updates on her project. And with that, I would like to thank Catherine again and introduce our second speaker, who is Dr. Pat Evans. Pat is a principal with CDM Smith in Bellevue, Washington. He has 30 years of research and development experience related to hazardous waste remediation, wastewater treatment, drinking water treatment, and energy. His current research includes wastewater treatment using anaerobic membrane bioreactors and microbial fuel cells, bioelectrical conversion of carbon dioxide to biofuels, anaerobic digestion of food waste, biological treatment for drinking water production, and treatment of emerging contaminants. Pat received his bachelor's and doctoral degrees in chemical engineering from the University of Michigan and also a master's degree in chemical engineering from Rutgers. Pat?
Thank you very much, Rula. It's a pleasure to be here. Hello, everyone. And so we're going to talk about microbial fuel cells for wastewater treatment. And while the topic of this seminar is forward operating bases, the microbial fuel cells really have applications beyond that, also in municipal, in industrial applications, and at fixed DoD installations in the United States. The overall goal of using a microbial fuel cell is to get to energy neutral or energy positive wastewater treatment and to be recovering these resources from the wastewater. So we're going to start off by talking about how does a microbial fuel cell work, talk about some of the components in the microbial fuel cell and how we've researched those to determine what the basis is for optimizing them and to be able to design and eventually manufacture them. Getting into continuous wastewater treatment and can we meet our regulatory goals for treatment of wastewater and discharge. Talk about some secondary polishing processes, and finally get into pilot scale testing and where we're going with that. So first, a microbial fuel cell is analogous to a regular fuel cell, with the exception we have a biological component in it. One of the components is the anode, shown right here, and we have a biofilm of bacteria that grows on this anode. And at this anode, what is happening is the fuel in the wastewater situation, it would be organic carbon, is being oxidized to products including carbon dioxide. When that oxidation occurs, it releases electrons. Those electrons can then go through a load. For example, it could be used for trickle charging of batteries, cell phones, or packs on troops. And then from there, the electrons, of course, need to go somewhere, and they go to the cathode, just as in a regular fuel cell. In this cathode, the oxidant is oxygen, and it is reduced into water. And we see here is a little cube-type microbial fuel cell with the cathode shown right here. This is one that was developed in Bruce Logan's laboratory at Pennsylvania State University. He's the principal investigator on this project. So in looking at the microbial fuel cells, we looked at a number of different components. One is the anode, which is shown here. We need to determine how many of them we need, what the size, what the orientation is. We also looked at the cathode, which is in red right here. And then a couple of other components. There is an item called the separator, which is between the anode and the cathode. The purpose of that is to protect the cathode, so we'll talk about that a little bit. And then there's a spacer. We need to get air or oxygen into the cathode, but at the same time we would like to have a modular system where we're putting these microbial fuel systems back to back, very much like we would have in a regular fuel cell, a stacked fuel cell. And to do that, if we make this chamber too small, the air won't be able to get in there and to provide oxygen to the cathode. So we need to research that as well. And then finally we get into our continuous flow testing and our engineering scale-up. So the research has been going on for many, many years, being led by Bruce Logan at Pennsylvania State University. Through that research has gone through a number of different generations of fuel cells, increasing in size. And the idea in doing that is, while learning how these different elements work, also being able to learn, well, what happens when you scale this up? This may be considered sometimes be, straight engineering, not research, but really there are a lot of very important research questions that we get into when we increase in scale. And so we've systematically increased the scale, going up as shown right here. So let's talk about the anodes first. What we have shown here, many of you may recognize this, it looks like a test tube cleaning brush. And actually this is a screenshot of a test tube cleaning brush. But what is different with the microbial fuel cell anode is, instead of this just being steel, this is made out of titanium. Otherwise it would corrode in a microbial fuel cell. And then the fibers here, instead of just being any old plastic, are carbon fibers, the electricity conducting carbon fibers. And what we have is the bacteria will grow on these fibers, and that's where they will develop those anaerobic conditions so they can anaerobically oxidize the organics in the wastewater and then transfer the electrons to these carbon fibers, which then can go up through the titanium wire up to our load and then to the cathode. So there are a number of questions here with these anodes. Should we have large diameter ones or small diameter ones? What's the distance between the anode and the cathode? Some of the plots I'm going to be showing you are similar to this. On the x-axis we have the current density, and this is in milliamps per square centimeter of cathode area. And so this is telling how much current we get in that cathode. The practical aspect of this is the larger the number, the better, because then we can have a smaller cathode and that decreases our capital cost. On the y-axis we have the power density. This is the milliwatts per square meter of cathode area. Here we want a larger number as well. And the idea here is to increase the amount of power that we get from that wastewater. And so what we can see here in two different anode configurations, this R8C, which is a small anode close to the cathode, versus the same size anode that's further away from the cathode, we find much better performance with this closely spaced anode. While not shown here, the larger anodes did not work as well. But this one worked quite well, getting up close to 1,000 milliwatts per square meter and almost 0.5, 0.6 milliamps per square centimeter. Now this was with acetate, which is not true wastewater. This is just a model compound that we use to be able to get reproducible results and consistent influent. But what happens with real wastewater? Well, the results change dramatically. We find that two replicate anodes, the exact same small diameter anodes, closely spaced to the cathode, do not perform similarly at all. And if we take a look at a different plot, which is the same axis here of current density, and then up here is the potential, we find these two curves, the blue and the green, this is the cathode. They're reproducing each other very well, indicating the issue is not with the cathode, it's rather with the anode. We have very different results. So what's happening is, with these small diameter anodes in the relatively weaker wastewater and more recalcitrant wastewater, is we have oxygen that is getting into the microbial fuel cell, and we're getting some aerobic degradation of the wastewater rather than power-producing anode respiring degradation. And so what we find is while these small diameter anodes may work fine with acetate, with real-world wastewater we need some larger diameter anode brushes, and so that's what we went with. Let's next talk about the separator. Again, this is the sheet. It can be thought of a woven cloth that is between the anode and the cathode. Its purpose is to protect the cathode. And so we did tests looking with a separator in blue and without a separator in pink. This is the power density over time. And you can imagine that as the power is high, we're getting a lot of COD removal. So what we see here is initially we're getting good performance, but then the power density decreases with the one with the separator. And this is because we're getting lower performance. With the one, this is the one without the separator, and we've removed all of the COD. Whereas the one with the separator, it's taking longer to treat our waste. So you think from this result that not having a separator, as in this case here, is a much better way to go. However, that's just the initial performance. If we take a look at long-term performance after 5 months, initially the results are very similar, both with a separator and without a separator. But if we take a look at long-term performance, when we have a separator, this performance is sustained. Whereas if we don't have the separator in there, we get fouling of that cathode, which is a maintenance problem, which increases our operations and maintenance costs. So we found that a separator really is critical when we're dealing with real wastewater, and we were able to, through additional experiments not shown here, find out what is the best type of separator to use. Now the spacer, this again is allowing oxygen to get to the cathodes, and when we have a modular or stacked cells of these anodes and cathodes, we'd like to have the spacer be as small as possible, so we decrease the entire footprint of our reactor. But we also have to have the spacer allow enough air to get in there so we get oxygen transfer to those cathodes. So we looked at 3 different types of materials for these spacers: a mesh, a plastic mesh, a column, which was just plastic columns here with the spaces in between, and then also a wire type of mesh. What we found here is we have the cell voltage in these lines right here plotted against current density, and over here is the power density in these curved lines. What we found is that the wire spacer worked the best, had the highest power density and the highest current density. The column was a little bit worse than that, but not too much worse. But the mesh was clearly inferior. And so from this, we were able to conclude that we need a wire spacer. The key here is to have a lot of open void and have minimal surface area contact between the spacer and that separator and the cathode. I've left the cathode for last. And the reason is because in many ways it's the most complex and most expensive part of the microbial fuel cell, and has been one of the most challenging parts. Traditionally, cathodes have been made using precious metals such as platinum, which are used in traditional fuel cells. However, this has an issue with fouling. In anaerobic microbiological systems, will produce sulfides, and these sulfides can poison these precious metals. And in addition, the platinum, of course, is expensive and a rare resource. And so Bruce Logan and his team came up with an alternative way to use polymer, polyvinylidene fluoride, as a binder, and then to hold our catalyst, which was activated carbon. There was also some carbon black there. And came up with a very innovative way called phase inversion, where this PVDF would be dissolved in a solvent that is also miscible with water, and then placed into a water bath. And at that time, the solvent would back diffuse into the water, leaving behind a mesh of this PVDF. very high open void area and allowing oxygen mass transfer to be very good in this area. And then we also would have a little skin of PVDF here that would be impermeable to water, and the purpose of this is so the water doesn't enter into this void airspace right here. So this worked quite well. And if we take a look at the performance, we find out it's very similar. Here's performance for the traditional platinum cathode, and here's the performance for this innovative cathode. So this worked quite well. So how well do these microbial fuel cells work when it comes to treating wastewater? We did tests at the Pennsylvania State University wastewater treatment plant, which is taking effluent from their primary treatment. So this is overflow from the primary clarifier going into our microbial fuel cell here, shown up in a blow-up. So here you can see there are 3 sets of cathode spacer cassettes, and then the anodes are on all sides of these. If we take a look at a little bit closer space, we can see right here is that size, and then we would have multiple of these units. So we did a lot of different experiments with these microbial fuel cells. Can't show you all the results, but one that I think was very interesting was looking at COD removal in percent versus the hydraulic residence time. What we found is independent of the configuration of the anode, the separator, and the cathode, and whether we would have flow upwards or downwards, all these different configurations, we saw similar performance and a similar dependence on hydraulic retention time. The greater the hydraulic retention time, the better COD removal. In certain experiments, we were able to get over 80–90% removal. Those data aren't shown here. And so, but what we did also see, in addition to this increasing dependence on hydraulic retention time, we would see a leveling off of the performance here as well. And so this is an issue, potential issue, in terms of being able to get to good effluent quality. It suggests we may need a polishing step downstream of the microbial fuel cell. But the other aspect of it is in terms of power. What we're trying to do here is, in addition to treat the wastewater, we're trying to treat it in a sustainable fashion where we are recovering energy from that wastewater and getting to energy neutral or energy positive performance. What we find that independent of the resistance, this would be the load that you would be charging, whether it's 1,000 ohms or it's a lower resistance at 100 ohms, we find that at high COD levels above 200 milligrams per liter, we get consistent current density. So we're getting good performance of this microbial fuel cell. But then as we start decreasing down in the vicinity of about 100 milligrams per liter of COD, in both cases, we find this current density drops off. And we find this is true with wastewater and with acetate. And so what we see here is that at the higher CODs, we are taking the energy potential in that wastewater and we're converting it into power. But as we get down to around 100 milligrams per liter of COD, which may be too strong for discharge, think of that as equivalent to 50 ppm of BOD, which is greater than the 30 milligram per liter EPA secondary treatment standard for BOD. We need a polishing step. And so, and also the reason that this is dropping off is because we're getting some air getting into our microbial fuel cell. So instead of getting microbial fuel cell and energy going through our load, we're just getting aerobic treatment, which can lead to greater sludge production. This is a problem as well. So there are a number of ways we can polish the effluent. One is an innovative technology that has been developed by Perry McCarty at Stanford University and Jae-Ho Bae at Inha University in South Korea. And this is called an anaerobic fluidized membrane bioreactor. Here we have hollow fiber membranes that have a pore size of 0.03 to 0.04 microns. This is a very, very mature technology and is used in wastewater treatment plants around the world and in drinking water plants as well. And then we pull the water through that, but before that, we have activated carbon in here to go ahead and keep these membranes clean. I believe one of the questions earlier was how do you keep the membranes clean? Well, this is one way to do it. You have granular activated carbon that is fluidized, and this rubs up against the membranes, keeping those membranes clean. Another way is to use biogas and sparge that here. That's not being done in this case. Well, in addition to this granular activated carbon keeping the membranes clean, it's also supporting a biofilm that can treat that residual COD. So we have our first stage of our microbial fuel cell that's removing maybe, say, 80% of the COD, and then we have the residual COD being removed with the anaerobic fluidized membrane bioreactor. In addition, we are filtering that sludge, so we don't need a large clarifier to remove that sludge, and we get high quality water, and we're seeing that we're getting very good performance, as we will see here in this next slide. Here's a picture of that anaerobic fluidized membrane bioreactor, and we see that about 50% of the COD was removed by the membrane, the microbial fuel cell, whether it's the total COD or the soluble. And then the remainder, with the exception of about 16 milligrams per liter in the permeate, was removed by this polishing step. And total suspended solids, very low, as you would expect in an ultrafiltration process. Now, so as I hope you've seen, we've learned a lot from these different components of the microbial fuel cells in terms of how to capture that energy efficiently and also to effectively treat the organics in the wastewater. How do we scale that up then? Well, we go back to our traditional engineering, chemical engineering, environmental engineering principles, and we say let's look at plug flow to maximize our first order kinetics. We can also put our cathode in here in a space where we use these also as baffles, and our anodes here, so we're getting this plug flow operation, and we're also minimizing short circuiting. But in addition, we also want this to be modular, so we can go ahead and mass produce this and make it economical. It needs to be scalable. And then a key part is we need to be able to maintain it, especially, this is true anywhere, but at a forward operating base, we can't have our soldiers spending all of their time cleaning our anodes and cathodes. We need to make it easily maintainable. So here is a design, preliminary design, showing these are cassettes where we have a series of anodes, and these cassettes can easily be removed and replaced with new cassettes. The cathode cassettes are shown right here. And this is the process that we're going forward in terms of pilot testing this. Speaking of pilot testing, the research I've shown you was funded under CERTUP. This new project is funded under ESTCP. Don Kropek with the U.S. Army is leading this, and Martin Page with the Army is also a very important part of this. And this demonstration will be done at Tobyhanna Army Depot in Pennsylvania. So it'll be close to Pennsylvania State University, so Dr. Logan's postdocs don't have to travel too much. And in that, we'll be using a biofilter downstream of that microbial fuel cell. So to conclude, we've been able to demonstrate that we can get energy neutral or energy positive power production with a microbial fuel cell. We are getting a little bit of energy being produced, 0.08 kilowatt hours per cubic meter water treated. Now to put that into perspective, activated sludge or extended aeration, an oxidation ditch, we're dealing more with consumption of 0.6 kilowatt hours per meter cubed of wastewater treatment. And if you look at the energy consumption for water treatment and wastewater treatment in the United States, it's about 2 to 4% of the nation's electricity demand. So it's not a small amount, and we must consider that. So if we can get to energy neutral, and even better yet, energy positive performance in treating our wastewater, this is good. And what we're doing is we're looking at converting these wastewater treatment plants into wastewater resource recovery facilities. The goal, we can easily get 50% COD removal, likely better than that, but we have to determine that we do need a secondary process, an AFMBR or a biofilter, and we can get to modular designs with this. want to acknowledge Bruce Logan, the PI on this project, and also Josh Goldman with CDM Smith, who did a lot of the engineering design on this project. And for additional information, you can see the project right here, the 2216, which is the CERTA project, and my contact information is right here. Thank you very much, and I'll be happy to entertain any questions.
Thank you so much, Pat. We did receive a number of questions for you, and we'll continue taking questions as you answer the next few that I'm going to ask you. Can you please explain whether electricity is the only product from the microbial fuel cell?
The electricity is one possible product in this configuration, but there are a number of other configurations that you can use microbial fuel cells. For example, Cesar Torres at Arizona State University, who's also been funded by CERTA, he's looking at a configuration where you use a different type of a cathode, and instead of producing electricity, you produce hydrogen peroxide. And that hydrogen peroxide can be used for oxidation of gray water or maybe even disinfection. In Australia, at a brewery, a full-scale microbial fuel cell is being used just to generate caustic. At the cathode, if you put an ion exchange membrane in there between the anode and the cathode compartment will become very high pH, above 12. And that caustic is used by this brewery for cleaning. And so that's very economical. There's also, this is a little bit more risky and further out there, but there's also the possibility of making liquid fuels and specialty chemicals. For example, Harold May at the Medical University of South Carolina has been funded by the Department of Energy, the ARPA-E group, and he's using the microbial fuel cell platform to produce hydrogen and then also liquid fuels that could be used to fuel vehicles.
Great, thank you. What do you think the prospect is for MFC commercialization, and what are some of the primary challenges in your opinion?
So I think MFCs it's a very exciting technology, a very exciting platform. There's been a lot of research on it. I think the prospect is good based on our understanding of how well they work and the more recent development of practical and expensive designs. But there are several challenges, and this is true with any innovative technology. We need investment by companies or organizations to be able to scale up the technology. Department of Defense through this program is clearly starting this, but more is needed in order to get it to the commercial level. Another aspect is risk management. You are going to have end users who they are looking for a technology that is going to work and provide good effluent quality, and they're going to depend on that, and there may be performance guarantees with that. You may have large engineering firms that need to follow those performance guarantees. So when you get into contracting, risk management needs to be considered, and we need to take into account that MFCs today, compared to some other technologies, are relatively higher risk, and someone needs to take on that risk.
Great, thank you. Are you aware of any companies that are selling microbial fuel cells right now?
There are a few. It's very much in its infancy. There is a company called Aquacell that is basing their design very much on the work that Bruce Logan and CDM Smith has done. But it's a very small size of a car battery, and they're putting multiple ones of these together. Cambrian Innovation in Boston is another company that's using their technology not so much as a microbial fuel cell, but more to boost methane in anaerobic digesters. And then an Israeli company called MFC, they have merged with RLW Water to form a new company called Fluence. And they do a lot of different things, and they may still be doing some work on microbial fuel cells. But these are still, I would consider, startup companies, and would say that we're not fully at prime time yet, but we're working on it.
Thank you, Pat. Can the system be configured to address primary treatment together with the associated sludge management?
It can. As part of the work that CDM Smith did along with Cesar Torres at Arizona State University, we came up with a fluidized bed bioreactor that would keep the solids suspended as they are being hydrolyzed and flowing through the bioreactor. This is the key aspect of doing primary treatment, is solids management, trying to prevent settling of these solids, so you're doing opposite of what you would have in a primary sedimentation chamber. But at the same time, you are, in addition to keeping those solids suspended, we need to maximize the hydrolysis of those solids in order to be able to get the energy that will be accessible to the microorganisms that are on the anodes.
Great, thank you. Can you provide information about the cost for this pilot and theoretically what it would cost for a full-scale system?
So the cost for this pilot test is about $1 million or so. Keep in mind that that is not the cost just for the equipment. This is the cost for doing the research associated with that. So a lot of sampling analysis, more than you would do in a traditional wastewater project. The cost of the equipment itself is on the order of about $300,000 for this pilot. And again, this is a relatively high cost because all of the anode or all of the cathode compartments need to be custom made. The idea is that as you would go to commercialization, these components would be made by polymer injection molding. And so for the capital cost of a full-scale system, we don't have that information yet. And the idea behind the ESTCP demonstration is to try to get closer to be able to estimating those capital costs. And in addition to that, operational and maintenance costs and life cycle costs.
Talking about the ESTCP demonstration, what is the status of the work that you're doing at Camp Tobyhanna?
Yes, so the process system is currently in its final stages of design, and we are also manufacturing the cathodes in an innovative process that is being done by a vendor for us. And there's the work plan that's being prepared, and we hope to get out to the field later this year or early next year.
Thank you, Pat. And one last question for you before we pull Catherine in. Can you tell us whether microbial fuel cells remove nutrients such as nitrogen and phosphorus, or is that only possible during tertiary treatment systems?
So microbial fuel cells will not remove nitrogen. They're going to be very similar to an anaerobic digester where your nitrogen containing organics proteins, they're going to be hydrolyzed and you're going to release ammonia. So you're going to need to deal with that ammonia downstream of the microbial fuel cell. Phosphorus, you can, while we don't have any data to support this, in the work that I've led on anaerobic membrane bioreactor demonstration under ESTCP, we found out that we do get some phosphorus removal that gets associated with the sludge, but we do need some downstream treatment to remove that phosphorus, for example, coagulation. Another aspect, and this applies both to MFCs and to anaerobic membrane bioreactors, is you can get sulfide, and a lot of it depends on the amount of sulfate that is present in your wastewater. And so that sulfide, in addition to releasing hydrogen sulfide gas, which is poisonous, and an odor issue, is a nuisance and needs to be removed as well. This may be very much lower in the microbial fuel cell than an anaerobic membrane bioreactor, but does need to be considered.
Great, thank you. And before we wrap this up, we did receive one more question for you, which is a little bit more technical in nature. Can you tell us what COD load is linked to the 0.0A 8 kilowatt hour per meter cubed of power production. What is that based on?
So this was based on an influent COD from several experiments, but about 600 milligrams per liter, give or take some. And then the hydraulic retention time was between 4 and 10 hours. So this hopefully gives you a general idea.
Great, thank you so much. And then when do you expect your project reports to be available? Is this something, if folks have a question, they can reach out to you and Bruce about, or is it already posted on the CERDP and ESCCP webpage?
It is already posted for the CERDP project right here. And so you can access the report right there. There are also a number of publications that you can access that if you go ahead and Google search Bruce Logan, you'll find his web pages, and he posts a lot of the peer-reviewed articles directly on his website. The ESTCP project, of course, they won't be posted until the project is complete.
Great, thank you, Pat. At this point, we want to wrap up with some broader questions and then pull Catherine back into that discussion. So I'm going to start out with a question, and Catherine, I'm going to ask you to please take a first crack at it. Can you please share with us your thoughts on what the environmental and economic drivers for development and adoption of new wastewater treatment technologies look like? Catherine?
Sure. From the economic standpoint, it's going to have to be pretty cost effective. To get into mainstream is going to, other than technologies are very different from what's commercially or often there. And so it's going to have to be very saving a lot of money, or in new development. I think a lot of these technologies will go. Environmentally, a lot of reuse is going to become critical, not just an option, but actually something that's required, because water resources are becoming more scarce, especially clean water they can draw potable from. So I think just a limiting reagent is going to be important there.
Thank you. Pat, what would you like to add?
Well, so it's the Water Environment Federation has made a big push in terms of just nomenclature. Instead of calling our facilities wastewater treatment plants, they're now encouraging us to call them wastewater resource recovery facilities. And a lot of municipal facilities are really going in that direction. And we're extracting resources. There's energy, nutrients, and carbon that can be reduced. Many plants are already recovering carbon in terms of the form of biosolids, which can be used as an agricultural amendment. There's certain companies like Astera that's recovering phosphorus. And then we also need to look at ways of increasing water reuse, either indirect or direct potable reuse. So we're making good strides in these areas, but we definitely need more adoption by all parties involved. Economic investment is always required. A big area is nitrogen removal. And I encourage you to take a look at a recent feature article by Perry McCarty on nitrogen removal. Current technologies are to use nitrification, denitrification, which is very energy intensive. And we now see alternative technologies such as nitritation, Animox, but often these are just used as side stream treatment. And we need to see, well, how can we implement this in our full stream treatment?
Thank you, Pat. What do the two of you believe is necessary for adopting innovative technologies in this area of work? Catherine?
I think the big portion of it, for the uptake of it, is going to be showing that it works, and especially when reuse is mentioned, getting over the perception that it is reused water and using the wastewater as a resource or a water source, non-traditional water source. And not just thinking, oh, it's reused water, but it's treated water, and actually in many cases is cleaner than water coming out of a drinking water facility.
Thank you. Pat?
I agree with those two things. I'll add three more. One is a risk management strategy. It needs to promote and not impede innovation. Again, think of what I said previously in terms of an end user. They need to be producing clean water for discharge that meets regulatory requirements and public acceptance. And so we need to figure out who's going to take on that risk. Second thing is investment, both time and money. And then a third thing, and sometimes this is maybe the most important thing, is you need a champion. You need a person in whatever organization is who's excited about this, and they're going to push this through. Doesn't mean you can't ignore those other 4 items that Catherine and I mentioned, but someone's got to be excited and be the champion.
Great, thank you. And as we get ready to wrap up, what last messages would you like to leave our audience with today? Catherine?
For me, mainly it's that we're not going to solve all the problems with one solution. We're going to need lots of research in lots of different areas and form the toolbox that works best at a certain site, but sharing the information to get it out there so you can make the most informed decisions possible.
Thank you. And Pat?
Yeah, I think for the work that we've done, consider microbial fuel cells as one technology that can be used to meet your wastewater treatment requirements and achieve energy neutrality. And consider this in strategic planning for your facility when going forward.
Great. Well, thank you both. This has been a great discussion. At this point, I would like to remind everyone that the next webinar in the series is in 2 weeks on Thursday, August 23. This webinar will feature Dr. Daniel Brown from Penn State University, who will present his work on developing the sediment volume search sonar, which is a novel detection system designed to increase our ability to detect unexploded ordnances in shallow waters. Registration is open for this webinar, so please visit the CERDUP and ESCCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. At this point, we would appreciate it if you can please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you so much for listening in.